Hello everyone. Today we are going to learn about the rate theory, the plate theory and system suitability parameters. This presentation is prepared by Atharva Joshi, Anushka Kamble, Aditi Kamthe and Tejas Khandekar. In chromatography, the theories like rate theory and plate theory helps us to describe how the separation process occurs, and the system suitability parameters are used to evaluate the efficiency and reliability of the chromatographic system. So first we are going to see about the plate theory. So the plate theory was initially proposed by Martin and Singe in 1941 to simplify the explanation of the separation process in the chromatography. It conceptualized the column as being divided into a series of imaginary theoretical plates, each representing an equilibrium stage where the solute distributes itself between the mobile phase and the stationary phase. It gives a hypothetical picture of the separation of the analytes between the mobile and the stationary phase. From the mobile phase is carried from one plate to the another and continues till it is eluted out of the column. The nature and the solute type determines the retention time and the peak width. As the theoretical plate number increases in the column, it narrows the solute peak and provides better resolution between different components in the sample. The number of the theoretical plate in a column is represented by n. A large n value indicates greater resolving or separation power of the column. This is what is referred to as the efficiency of the column. The efficiency of the column is represented by HETP, that is height equivalent to a theoretical plate. This is the length of the column divided by number of theoretical plates. A lower HETP indicates better separation efficiency as it suggests more equilibrium stage per unit length. Its formula is H equals to L upon the N, where N is directly proportional to 1 upon the H and N is directly proportional to the column efficiency. Plate theory is somewhat limited because it assumes that each theoretical plate reaches equilibrium instantaneously, which isn't always realistic. It is generally used to get an initial understanding of the column efficiency. Now we will going to see about the rate theory of chromatography. Of the chromatography process accounts for the fact that solute molecules need time to diffuse and interact with the stationary phase, and it considers the flow rate of the mobile phase. So the rate theory shows that when solute elutes out of the column, it impacts the band shape and is affected by the elution rate. It provides information about the shape and the breadth of the elution band. It gives a realistic explanation of the process occurring in a chromatographic column. It considers and measures the time taken by the solute to equilibrate between the stationary and the mobile phase. The rate theory of chromatography is expressed mathematically by the Van de Meter equation. Rate theory is often expressed using the Van de Meter equation, which describes the relationship between the height equivalent to the theoretical plate, that is HETP, and the linear velocity u of the mobile phase. So the equation is HETP equals to A plus B upon the nu plus Cm plus Cs into nu. So from the graph we can clearly understand the Van de Meter equation where plate height is plotted against the flow rate. So A equals to the AD's diffusion parameter, B represents diffusion coefficient of eluting particles in the longitudinal direction, C is the resistance to the mass transfer coefficient of the analyte between the stationary and the mobile phase, nu is speed, Cm represents a dispersive connection in the mobile phase, Cs is sorption and desorption of the solute from the stationary phase, where HETP is the measure of zone broadening. See the system suitability parameters. It is defined by ICH as the checking of a system before or during the analysis of the unknown to ensure the system performance. It verifies that the system is working correctly before the actual sample analysis. The testing limits should conform to the guidelines provided by CDER, that is Center for Drug Evaluation and Research. Other sources for referencing includes the USP and the ICH. So the different suitability parameters includes the resolution, retention time, pressure, column efficiency, repeatability, plate tailing factor, and signal to noise ratio. So the first parameter is the resolution. The resolution is a quantitative measure of how well the two illusion peaks can be differentiated in the chromatographic separation. Resolution is generally defined as the difference in the retention time between the two peaks divided by the combined width of the illusion peaks. It can be represented by the formula as capital R equals to 2 in bracket TR2 minus TR1 upon W1 plus W2. The next parameter is the retention factor. In chromatography, the retention factor is the fraction of an analyte in the mobile phase of the chromatographic system, and in planar chromatography, it is defined as the ratio of distance traveled by the center of the spot, that is the solute front, to the distance traveled by the solvent front. As from the figure, it can see that retention factor RF is equals to Zx upon Zf minus Z0. Now we will see how the pressure affects different parameters. First, flow rate. Increased pressure can lead to a higher flow rate, which can result in a reduced retention time and decreased separation efficiency. Column packing. High pressure can cause the column packing material to compress, which leads to channeling, reduced porosity, and decreased in the column efficiency. Particle size. Pressure can cause smaller particles to become compacted, leading to reduced surface area and decreased column efficiency. Stationary phase. Pressure can affect the stationary phase, causing it to become distorted or compressed, leading to reduced interaction with the mobile phase and decrease in the column efficiency. Mobile phase. Pressure can affect the mobile phase, causing it to become compressed, leading to changes in viscosity and density, which can impact the column efficiency. Column dimensions. Pressure can cause the column dimensions to change, leading to altered flow dynamics and decreased column efficiency. Fittings and connections. Pressure can cause fittings and connections to become loose, leading to leaks and decrease in the column efficiency. To mitigate these effects, it is essential that certain things to be considered, like optimize the column packing, use appropriate particle size and stationary phase, control the flow rates and the pressure, monitor the column dimensions and the fittings, perform the regular maintenance and the column conditioning. The other parameter we can consider is selectivity, which is represented by alpha. It measures how well the column distinguishes between the two analytes. By understanding and addressing these factors, we can minimize the impact of pressure on column efficiency. Repeatability refers to the consistency of the results when the same procedure is performed multiple times under the identical conditions. It ensures the reliable measurement of the drug potency and purity. It reduces variability in the results, which leads to better reproducibility in the experiments. The key factors which influence the repeatability are instrument precision and calibration, sample preparation techniques, environmental conditions like temperature and humidity. Plate number, which is also referred to as number of the theoretical plates, denoted by capital N. It is a parameter which indicates the efficiency of a chromatographic column in separating compounds. Higher plate number indicates the better separation and resolution of the components. Aim is for higher plate numbers to enhance the method performance. Factors which affect the plate number includes column type, mobile phase composition, and flow rate. Plate number is represented by the formula, that is capital N equals to 16 in bracket TR upon W the whole square. Factor denoted by capital T. It evaluates the symmetry of the peak. Tailing occurs when some sites on the stationary phase retain the solute more strongly than other sites. Peak fronting is the result of overloading the column with a sample. Injection of too much sample and overloading affects the results from the poor sample solubility in the stationary phase as too much sample is injected. It occurs when the peak symmetry factor, that is AS, is greater than 1.2. Although peaks with AS greater than 1.5 are acceptable for many. Parameter is signal to noise ratio. It is the ratio of the signal to the noise in the liquid chromatography separation. calibration. Signal to noise ratio is important when it contributes to the error of chromatographic measurements. This is usually the case when the signal to noise ratio is less than 100. To improve the signal to noise ratio, we can increase the signal, decrease the noise, or inject more sample. We can try changing the column, such as using a shorter column or a column with a higher plate number. We will see the system suitability testing limits. According to CDER guidelines, the repeatability of the peak response should be less than or equal to 1% for 5 replicates. Resolution should be greater than 2 general. Tailing factor should be less than or equal to 2. Column efficiency greater than 2000, that is plate count. Capacity factor greater than 2. According to HSU and chain recommendation, repeatability of the peak response should be less than or equal to 1.5% general, 5 to 15% trace, less than 5% biologics. Then resolution, it should be greater than 2 general and greater than 1.5 quantitation. Tailing factor should be less than 1.5 to 2. Column efficiency, the readings are not available, and the capacity factor should be in between 2 to 8. System suitability parameters are crucial for maintaining data quality, ensuring reproducibility, and providing the confidence in the results of chromatographic analysis. So, these are all the different theories like the rate theory and the plate theory for the chromatography and the system suitability parameters. Thank you.